Hello viewers, welcome to add-on. In this question, we are asked to draw half-wave and full-wave rectifier with the output voltage waveform. Okay, so let us start. So, a rectifier, these are of two types, half-wave and full-wave rectifier. Now, what is the objective of this rectification? So, rectification, rectification, it is the process of the conversion from AC to DC, which means if we are applying AC voltage at the input side of a rectifier of half wave or full wave rectifier, then the output voltage that we will be getting is purely DC. So this is the objective of the rectification. And by AC, it means alternating current, which means the value of the current will alter or changes with respect to time. And in DC, the value of the current will remain the same with respect to time. Okay. So let us start with the half wave rectification process. So suppose this is the input voltage wave, which is varying like this. This is passed through a half wave rectifier. Okay. So then the output voltage will be like this. As we can see, at the input side, the voltage waveform had a positive half cycle as well as a negative half cycle. But in the output side, we are only getting the positive half cycle portion. This is because this is the half wave rectifier, and half wave rectifier only rectifies the half cycle of a full cycle variation. Okay, suppose this is a full cycle variation, it will rectify only the half cycle, which means for the positive part, we will be getting a positive waveform. And for the negative portion of the waveform, we will also get a positive portion of the waveform. Okay, so this is the main reason it is known as a half wave rectification. Okay, and we can also say in the half wave rectification, either the positive half or the negative half is passed while the other half is blocked, and it requires a single phase power supply. So suppose this is the circuit diagram of a half wave rectifier. This is the simple circuit diagram. This is the load resistance. Across the load resistance, we will be taking the output voltage. This is the input voltage or AC voltage that we are applying. And this is the plain rectifier circuit which can be made using a PN junction diode. Okay. So how this circuit operates, we are going to discuss about that. So this is a PN junction diode. This is a P side. This is the N side. And this is the alternating current voltage supply. So when the P side of the diode is connected to a positive terminal of the battery, then the PN junction will be forward bias, which means the diode will conduct. Okay. So for the positive half cycle, okay, for the positive half cycle, which means this is a full wave, this is a full wave power supply. This is the positive half cycle. This is the negative half cycle. So for the positive half cycle, okay. So for the positive half cycle, the PN junction diode will be forward biased, because when the P terminal is connected to the positive terminal of the battery, then the diode will be forward biased. And when the diode is forward biased, current will flow through the circuit like this, and we will be getting a output voltage. Okay. So for the positive half cycle, like up to this part, we will be getting a output voltage. Okay. And during the negative half cycle, what happens is that the value of the polarity is like this. For the positive half cycle, this is plus, this is minus. This is because the value of the voltage is continuously increasing in the positive half cycle, and it is also above the zero reference line or ground level line. Okay. But in the reverse biased, the polarities become opposite. This becomes negative and this becomes positive, because during reverse bias, the value of the voltage will decrease or fall below the zero level line or the ground reference line. So during this time, the polarities will change. So before, the polarity was plus minus, and now the polarity become minus plus. So when the P terminal is connected to the negative end of the battery, the diode becomes reverse biased, and during that time, no current will flow through the circuit. As a result, for this negative half cycle, we won't be getting any kind of output. Okay, we won't be getting any kind of output. And again, if there is a positive half cycle present, we will be getting an output. Okay. So as we can see, it is only rectifying only the half wave cycle. Okay. So this is the input voltage and this is the output voltage. Okay. So this is the main purpose of a half wave rectification. Okay. And now the few things that we need to understand in the half wave rectification is the peak current, or we can say the average current in a half wave rectification process. The peak current or average current in the half wave rectification process is, I can say it I of average, it is equal to Im by pi, and the RMS value, the RMS value is I of RMS is equal to Im by 2. Okay. So there is the average value and RMS value. And one thing we need to know is the ripple factor. Okay. Ripple factor. Now, what is the ripple factor? Ripple factor is, we can see in the rectification process, I have said, it is the process of conversion of AC to DC, which means alternating current to direct current. But as we can see here, these two waveforms, one is AC, and we cannot say that it is purely DC. Why? Because the value of the current is varying here with respect to time. And why this happens? Because the AC component which was present in the input waveform is still present in the DC component as well. So due to this presence of the AC component in the DC waveform, these variations are occurring, and this is known as a ripple. And how do we calculate the ripple factor? I am representing the ripple factor by gamma. Gamma is equals to I of AC divided by I of DC. It means how much AC component is present in the DC output waveform. Okay. And it is also equal to root over I of RMS divided by I of DC whole square minus 1. Okay. So the value of I of RMS is this, and the value of I of average is this. If we put the value here, it is 1.21. Okay. So this is the value of the ripple factor for half wave rectifier, and efficiency for half wave rectifier is almost about 40%. Okay. So this is the main principle for the half wave rectifier. Now we will discuss about full wave rectifier. Now full wave rectification, it produces the output voltage for both positive half cycle as well as negative half cycle. So for positive half cycle, we will be getting output voltage, and as well as for negative half cycle, we will be getting a output voltage here. And sorry, I mistake one thing here. This is not for half wave rectifier. This is a normal rectifier. Okay. And we can also say this is a full wave rectifier. Okay. Because in a full wave rectifier, we will be getting output voltage for both positive half cycle as well as negative half cycle here. Okay. So this is a full wave rectifier. So in the full wave rectifier, we are getting the output voltage for both positive half cycle as well as negative half cycle as well. Okay. So this is the main purpose of full wave rectifier. It is particularly of two types: center tapped and bridge rectifier. Okay. Center tap rectifier and bridge rectifier. So these are the main two types of the full wave rectifier. Now we will see the circuit diagram of this two type full wave rectifier. So in a center tap rectifier, we are gonna draw a transformer here. This is coupled with another transformer. This is a diode. This is a diode. And there is a load resistance connected here. We will be taking the output voltage across this load resistance. This is point A, this is point B, this is diode 1, this is diode 2. Okay. And this is the AC input here. Okay. So for the positive half cycle, okay, for the positive half cycle, this is a center tap rectifier, which means this is tapped at the center. So for the positive half cycle, suppose for this positive half cycle, due to this center tapping, the voltage, or we can say the polarities at the other end of the transformer will become like this. On the one side of the tapping, we will be getting positive, negative, and on the other side of the tapping, we will be getting positive, negative. Okay. So we can see here, this diode 1 is connected to the positive terminal, and this diode 2 is connected to the negative terminal. And to be specific, the P side of this diode 1 and the P side of this diode 2 are connected to the positive and negative terminal. And as I have said, if the P terminal is connected to positive, if this P terminal is connected to the positive pole of the battery, then the diode will be forward biased. And if it is connected to the negative pole, then the diode will be reverse biased. So for the positive half cycle, okay, for the positive half cycle, the diode 1 will conduct. Okay. So at the output, we will be getting a voltage for the positive half cycle. Now, what happens during a negative half cycle? During the negative half cycle, as I have said, the polarity will change. So the positive negative will now become negative positive. Similarly, here the polarity will become negative positive and here it will become negative positive. So we can see the P terminal of the diode 1 is connected to the negative pole. So during this time, diode 1 will not conduct. But in diode 2, we can see the P terminal of the diode 2 is connected to the positive terminal. So during the negative half cycle, diode 2 will conduct. And as the diode 2 will conduct, we will be getting a output voltage here. Okay. So in the half wave rectifier, we are only getting the output voltage for this positive half cycle. But in the full wave rectification, we are getting the output voltage for both positive half cycle as well as negative half cycle. Okay. So this is the explanation of the center tap rectifier. Now we will discuss about bridge rectifier. Okay. So the circuit diagram of bridge rectifier is like this. Sorry, one second. Okay. So this is the circuit diagram of a bridge rectifier. This is the AC input power supply. Okay. So across this is the load resistance RL from which we will be taking our output voltage. And these are the 4 diodes which are connected. Diode 1, diode 2, diode 3, diode 4. Okay. So what happens in a bridge rectifier for the positive half cycle? At this particular node, we will be getting a positive pole of the battery or we will be getting the positive terminal. And at this pole, we will be getting the negative voltage. Okay. Because this is the AC input voltage. At this side, we will be getting the positive power supply and this is the negative power supply. So we can see the N terminal of the diode 1 will be connected to the positive side and the P terminal of the diode 2 is connected to the positive side. Okay. And as I have said, if the P terminal is connected to the positive side, then it will be forward bias. And if the N terminal is connected to the negative side, it will be forward bias. If P is connected to negative or N is connected to positive, it will be reverse biased. So here, the N terminal of the diode 1 is connected to the positive pole and the P terminal of the P terminal of this diode is connected to the positive pole. Okay. So this diode will be forward biased and this diode will be reverse biased. Okay. And similarly for these two diodes, the N terminal is connected to the negative pole and the P terminal is connected to the negative pole. So this diode will become reverse bias and this diode will become forward bias. So for the positive half cycle, these two diodes will conduct. As a result, for the positive half cycle, we will be getting the output waveform. And similarly for the negative half cycle, we will be getting negative polarity here and positive polarity here. So during this two time, this diode, this N terminal is connected to the positive pole, negative pole. So this diode will conduct and the P terminal is connected to the positive pole of this battery of this diode 3. So during this time, diode 1 and diode 3 will conduct and for the negative half cycle as well, we will be getting the output voltage. Okay. So this is the main principle of the half wave rectifier and a full wave rectifier. Okay. Now, if we want to discuss the average value and RMS value, I of average in this case is 2 of IM divided by pi and I of RMS is equals to Im divided by root 2. Okay. And the ripple factor here, which is gamma, this is equals to 0.48. Okay. As we know, in the half-wave rectifier, the ripple factor was 1.21. So we can see the ripple factor has been reduced by a much in the full wave rectifier, because in the full wave rectifier, we are getting the output voltage for both positive and negative half cycle. So the current, suppose here in this case, for the half wave rectifier, the output voltage was like this. So the current that we are supposed to be getting was like this. Okay, this straight line. So the ripple can be represented like this. So this is the ripple. Okay, this curvy waveform that I am drawing here, this is the ripple. But in the half wave rectifier, we are getting output voltage like this. And if this is our desired voltage, which is this straight line, we can say the ripple is like this. Okay. So we can see the ripple here is much more high than the ripple here. Okay. So the ripple in the half wave rectifier is much more greater than the full wave rectifier. So the ripple factor is 1.21 here and the ripple factor is 0.48 here. And the efficiency of the full wave rectifier is 81.2%. Okay. So this is all for half wave and full wave rectifier. Thank you.